Hello everyone. So in this video we look at the previous year paper solutions for UGC NET 2013 paper 2, right? June. This is solutions for June 2013. So in consequent videos we are going to see solutions of different papers. Also we are recording lectures alongside. So you can refer anything, any concept that you do not understand in previous year paper, you can refer to the respective lectures of that subject. If after that also you have any doubts, you can just leave us on comments. For any further inquiries, you can call us on the numbers given in the details. And for admissions also, call us on 9821876104/02. Thank you. So we start with the first question now. So they're asking an intrinsic semiconductor, what is the ratio of electron density to the hole density? That is, they're asking you about the relation between electron density and hole density in intrinsic semiconductor. So we're going to see what is intrinsic. What does intrinsic mean? Now see, intrinsic basically means no doping. Intrinsic in English means pure. This word means pure, without mixing, without impurity. So intrinsic means no doping. We are not adding additional electrons or holes. We are not adding any acceptor or donor atoms, which means that what is going to happen in intrinsic semiconductor, number of holes and number of electrons is going to be equal. Number of electrons is going to be equal to number of holes. So if you just look at the options, this is going to be option D. Electron density is same as the hole density. There is no doping, no impurity, no added acceptor or donor atoms. See, what happens in a semiconductor is anyway electrons and holes are not going to be equal. There is practically no intrinsic semiconductor. There is going to be some mixing, some doping. It occurs due to manufacturing defects. Okay, whenever you are cutting a crystal, whatever, there are going to be some defects. But what do we consider? Ideally, we consider that in an intrinsic semiconductor, number of electrons and number of holes are going to be same, right? Fine. Now look at the next question. So they are asking you, PN junction diode can be used as oscillator, amplifier, insulator or rectifier. So you know the characteristics of PN junction diode. What happens is PN junction diode allows current only in a single direction, right? It allows current only in a single direction. These are how characteristics, okay, approx characteristics of PN junction diode. What happens in reverse bias? Reverse bias means whenever you're giving negative voltage to this, then current is not going to increase, right? These are the VI characteristics of PN junction diode, right? Now if just see here, see, this is voltage, this is current. So whenever you're giving negative voltage means whenever you're trying to give voltage in opposite direction, what is going to happen? Current is going to increase drastically, which will lead to breakdown of the diode. Breakdown of the diode means it will stop working, okay? So it is going to allow current only in a single direction. So what happens basically is, suppose you're giving some waveform like this as input. Okay, this was my input, suppose. Fine. Now what is going to happen? When you're going to apply it to this PN junction diode, it is going to allow current only in a single direction. The other direction is not going to be allowed. So what happens? Current is going to flow in single direction. So this is basically half wave rectification. Half wave rectification means this pulse which was applied here has been rectified, was not allowed, could not pass. So this is what happened. This is half wave rectification. Although full wave rectification means something like this. This is also possible using PN junction diode. You have to connect two diodes. Anyway, that is a different topic. So basically PN junction diode is used as a rectifier. So the correct option is going to be option D. Okay, fine. Now look at the next question. Norton's equivalent form in any complex impedance circuit consists of equivalent current source with the equivalent resistance, equivalent voltage source in series with equivalent resistance, equivalent current source in parallel with equivalent impedance, and equivalent voltage source in series with equivalent impedance. Fine. So when we looked at Norton's theorem, we saw that what happens in Norton's theorem is all the circuit sources, all the sources, current source, voltage source, are simplified as one singular equivalent current source in parallel with equivalent impedance. and here you are going to apply the load, right? Between these points you can apply load. So this is what happens in Norton's equivalent, right? See, if you just talk about this option B, okay, fine. So which is this option going to be? This is going to be option C, equivalent current source in parallel with equivalent impedance. So do not confuse between impedance and resistance, okay? Since we are applying this in parallel with some source, okay, so we consider impedance. Now if you look at option B, equivalent voltage source in series with equivalent resistance, this is basically the statement of Thevenin's theorem. This is going to be Thevenin's theorem. In Norton's theorem, we are considering this current source and equivalent impedance. Okay, in Thevenin's theorem, we are considering voltage source and equivalent resistance. Fine. Right. So this was just a theory question. Look at the next one. Zener diode is up. So Zener diode is basically a reverse bias diode. See, this Zener diode can be used in forward biased also, but then it loses its uniqueness, okay? It behaves like any other ordinary PN junction diode only. What is the specialty of a Zener diode? It is a constant voltage diode, okay? You keep on increasing the current through this diode, still it is going to give you a constant voltage across it. Voltage across this diode does not change even if you keep on increasing the current across this diode. Fine, you must have looked at characteristics of a Zener diode. So what happens in forward bias? This behaves like a normal PN junction diode. But what happens in reverse bias is, this is the knee current. Okay, after this knee current, this has the characteristics like this. Okay, so basically what is happening? Even if you keep on increasing the current through this diode, okay, in reverse bias, see, we operating this in reverse bias only. Even if you keep on increasing the current through this diode, voltage, this is the Zener voltage, so this voltage remains constant. So we using it in a reverse bias only. In option B, if this would have been constant voltage source, actually it is not a source, but yes, it maintains a constant voltage across it, okay. So among these options, option A is going to be the correct one. It's a reverse bias diode. Right, now look at the next question. Which of the following oscillators make use of both positive and negative feedbacks? Hartley oscillator, Colbert's oscillator, phase shift oscillator, Wien-Bridge oscillator. So the correct option for this one is going to be Wien-Bridge oscillator. So what happens in a Wien-Bridge oscillator? We are having both positive and negative feedbacks, right? If you have looked at the architecture, you must be knowing this uses both positive as well as negative feedbacks, right? So look at the next question now. So they are asking, superposition theorem can be applied only to circuit having. See, when you have learned about superposition theorem, you must have seen that if there is any passive or non-linear or linear bilateral elements present in the circuit, the superposition theorem cannot be applied. Only if you are having independent current or voltage sources and resistive elements, only then we can apply superposition theorem, right? So out of the given options, A option is going to be the correct one. Only you are having resistive elements or independent current and voltage sources. You should not have any passive elements, you should not have any non-linear elements, and you should not have any linear bilateral elements, right? Then only you can apply superposition theorem. Fine. So look at the next question. Identify the fastest analog to digital converter. See, if you have studied ADC, then in parallel conversion, what happens is, parallelly there is going to be we are going to have one circuit which is going to convert this analog signal, your analog signal, parallelly to digital binary output, okay. So in parallel conversion, time taken for conversion from analog to digital is minimum time. Okay, this dual slope integration is going to take maximum time. This is going to take maximum time, but going to give most accurate result. So this gives most accurate result. Okay, ramp conversion is going to take more time than this less time than this dual slope, more time than parallel conversion. Okay, and what happens in successive approximation? This takes fixed time. This is going to take fixed time always going to take fixed time. Any input you give, this time is not going to vary, okay, and gives approximate result. So this parallel conversion takes minimum time. Okay, this is fastest, right? So look at the next question now. 1K memory device contains how many memory cells? Fine. See, 1K refers to 2 to the power 10. Okay, this K means 2 to the power 10, which is actually equal to 1024. So in 1K memory, there are going to be 1024 cells, 2 to the power 10 cells. So option B is going to be the correct one here, right? 1K means 2 to the power 10 cells. Fine. Now look at the next question. Which logic function has the output low when both inputs are high? Okay, so we can just make a truth table here and see the logic function. Since there are two inputs, these are going to the possible cases. Now this output should be low only when means we're talking about only one case, both inputs are high, which means this one. When both inputs are high, we want output to be low. If you just write this function as, this is what is it going to be? AB bar. See, I'm writing it from here only, okay? I'm writing it from this cell only. This AB bar, which is actually representation of a NAND gate. So, NAND logic function has output low when both inputs are high. See, anyway also, you know that what happens in AND, okay? It has output high when both inputs are high. Now, we want output low when both inputs are high. That means we have to put a bar. So this is going to be NAND function. Right, look at the next question. In FM, when frequency deviation is doubled, then what happens to modulation index? See, what is the modulation index in FM? Modulation index in FM is actually delta F upon FM. This delta F is frequency deviation. This FM is modulation frequency. So when you double this frequency deviation, that is if delta F doubles, what happens? Modulation index is also going to be doubled, provided that modulation frequency does not change. Okay, if this modulation frequency does not change, then modulation index gets doubled. Fine. Look at the next question. So they're asking you about volatile memory. See, first you try to understand what is volatile memory. Volatile memory means as soon as the system is switched off, as soon as power is taken off, power turns off, okay, you're going to lose that memory. Memory is gone. Okay. Volatile means it will disappear, it will go away. Non-volatile means either you switch on power immediately, you switch off at random. Memory is going to stay. Okay, memory does not go. So ROM, which is read-only memory, okay, that is why its name is read-only memory. You cannot make changes to this memory. This is a non-volatile memory. Non-volatile means even if power goes off at random, this memory is going to stay. However, RAM is random access memory. So what happens in this memory is, you can make changes to this memory, okay, but if you have not saved your changes, then power goes off, this memory is going to disappear. This is actually your volatile memory. So out of the given options, your RAM is going to be a volatile memory. See, if you talk about this magnetic disk or ferrite core, these are different types of memory that have been used before, okay, they are not in a lot of use nowadays. So magnetic disk and ferrite core, these are permanent storage memories. Once they have been written, they cannot be overwritten, okay. However, in semiconductor type memories, the memories that have been used in your systems nowadays, these are rewritable memories. That is, you can erase your data and rewrite these kind of memories. These kind of memories cannot be written, okay. So there is no question of volatile or non-volatile. Fine. So the correct option is going to be option D, semiconductor RAM. Right. So look at the next question now. An SCR can be formed by using. So SCR is basically a combination of one NPN and one PNP transistor. Okay. What they are doing is, they are connecting a PNP and NPN. They are connecting this P of this transistor to P of this transistor. Okay. PN diode they are taking in common. PN diode, one PN diode is going to be forward bias, one PN diode is going to be reverse bias, and they are connecting this and forming an SCR, right? So this SCR is going to contain one PNP and one NPN transistor, right? So again they are asking you pH of human blood. So pH of human bandwidth is basically between 7.5 to 8. Okay, there is nothing much in explain in this question. So come right to next question. So they're asking what is SIM. See, this is actually, they're not talking about your mobile SIM. They're talking about, this is an instruction in 8085 microprocessor, which is set interrupt mask. Set interrupt mask. So what is happening basically, 8085 has a number of interrupts. Okay, you're having number of interrupts in 8085. However, you can mask. Mask means delay or stop some interrupts from coming using this instruction of SIM. Another instruction we are having, which is read interrupt mask, so that you can know the status of those interrupts. Fine. So basically this SIM, you're giving this instruction SIM. What is going to happen with this SIM? You're going to give some values. Okay, going to give some values to store in accumulator. After that, you give this instruction SIM. Then some interrupts can be masked or unmasked. Okay. So this is basically set interrupt mask. Fine. So they're saying that quantization noise occurs in TDM, PCM, FDM or WDM. So what is quantization noise? Basically, see, when you are having an analog signal is going to have any possible value, right? It is going to have a set of values. Now when you want to convert it into digital set of values, that is, you want it to take a particular number of values. What am I saying is, suppose you had a signal like this. Fine. You want it, so this signal has all the values from 0 to 1. Right now you want it to take only, suppose 3 values, 0, 0.33, 0.66 and 1. Okay, maybe 4 values, whatever. So you want to take it only 4 values. Now what do you have to do? You have to assign all these values, all these levels from 0 to 0.3 must take value 0.3. All these levels between 0.3 and 0.6 must take value 0.6. Whatever your scheme is. Right. Now because of this procedure, because you allotted some analog values to fixed levels, this process is known as quantization. This is basically what happens in quantization. So it is a big process how this happens, what is happening, but this is what basically happens. Now due to this approximation, what happens, some noise adds. Okay, some addition of noise is going to take place. Now as you can see, more the number of levels, less is going to be the noise. If you make very less levels, if I make only 2 levels out of this, noise is going to be more because more approximation, right? If I take more number of levels, noise is going to be less. So this noise, this type of noise which occurs due to approximation is known as quantization noise, and it occurs in PCM. PCM is pulse coded modulation. So this is going to occur in PCM. Why? Because in PCM we are applying this analog signal and we want digital output, right? So answer is going to be B, PCM.